Hi, welcome everybody to the science class. Something that I've been noticing for a bit is people are having trouble with significant figures. So I figured I'd come up with some sort of practice. That way we'd be able to work out some significant figures problems and identifying the different significant figures per number. All right, so let's go over a couple of the rules. So all non-zero digits are indeed significant. So if we look at the number 546, we see that the 5, the 4, and the 6 are all non-zero digits. Therefore, there are 3 sig figs. Strange in that number. Now, if we look at 7,893, 7,893, all of the digits in this number are indeed significant because they're non-zero digits. So therefore, I have 4 sig figs here. Looking at 0, 0, 1, 2, 8. 1, 2, 8 are non-zero digits. And the 0, because they're in front of non-zero digits, all zeros in front are not significant. So therefore, there are 3 significant figures within this number. Now looking at a simple example is 23, 2, and 3, both non-zero digits. Therefore, there are 2 significant figures in the number 23. Starting off pretty easy. Again, all non-zero digits are significant. All right, let's look at something a tiny bit more complicated. All zeros in between non-zero digits are significant. So if we look at the 7 and the 7, there are 3 zeros in between. Now, because they're sandwiched in between non-zero digits, all the digits in this number are significant. So that's 1, 2, 3, 4, 5, given 5 sig figs. Now let's take a look at 80,305. Well, we know all non-zero digits are significant, and these zeros are sandwiched between non-zero digits. So therefore, these are also significant. So now we have 1, 2, 3, 4, 5 significant digits in this number as well. Now let's take a look at this number right here. All these zeros are sandwiched between non-zero digits. So therefore, we have 1, 2, 3, 4, 5, 6. So now we have 6 significant figures within this number. One final example, let's take a look at 34050. This 0 is sandwiched in between non-zero digits. This 0 is sandwiched in between non-zero digits. We're going to see in a second why this is not significant. But all zeros that are not sandwiched in between non-zero digits are up for question. So therefore, this number has 1, 2, 3, 4, 5 significant digits. Now let's try to look a little bit further to see why these zeros are in question, how we can determine if they're significant or not. So then we turn to the Atlantic Pacific rule. So this is the third rule. All other zeros use the Atlantic Pacific rule. This takes a little bit of knowledge of geography. So this is the Pacific side of America, and we start on this side if the decimal is present. Now for the Atlantic part of the rule, this is on the other side of the country. This is where we start if the decimal is absent. Let's take a look and find out exactly how this works. So if we look over here, there are no decimal points. So this is just 24,000. These zeros are not sandwiched in between non-zero digits, so these are up for question. Now, because the decimal point is absent, we're going to use the Atlantic rule. So we're approaching from the Atlantic side, and then we stop once we hit a non-zero digit. I'm going to draw a line over here. Now, everything on the other side of this line, starting from the Atlantic towards the Pacific, are significant. Now, we already know that these were significant because they're non-zero digits, but these zeros are not significant because they're on the right side, or the Atlantic side, of our dividing line. So therefore, this number only has 2 significant digits. Now let's take a look at 6,000. Now the decimal point is present. There are no non-zero digits on the right-hand side, so therefore we're just going to draw our line at the decimal point. Now everything to the right is significant. These numbers, because they're 4 before the decimal point, are indeed significant because the decimal point is present. So therefore, we're using the Pacific side of the rule. So therefore, there's 1, 2, 3, 4, 5, 6 significant digits in the 6,000 number 0.00. Let's take a look at another example. 0.000544070. Now remember, all non-zero digits are indeed significant. So we know we have 3 right off the bat. We know that this 0 is significant because it's sandwiched in between non-zero digits. Therefore, all the other zeros are up for question. Now, because the decimal point is present, we're going to be using the Pacific rule, starting from the Pacific side, going our way down until we hit a non-zero digit. First digit that we're going to hit is this 5. Now, because we're using the Pacific rule, everything to the right, heading towards the Atlantic, starting from the Pacific side, is significant. So therefore, 5, 4, 0, 7, 0 are all significant. So that gives us a total of 5 significant figures. Let's take a look at another example of 7.2400. Now, the decimal point is placed over here, and we stop at the first non-zero digit. Well, that's 2 in this case. So we're going to be heading this way, and everything to the right is indeed significant. Now, the 7 is going to also be significant in this case because it's a non-zero digit. So altogether, we're going to have 1, 2, 3, 4, 5 significant digits in this number. Now let's take a look at rounding significant figures. So this is commonly tested on unit tests or state assessments. So this is important that we get the hang of this. So the question is to round the following numbers to 3 significant digits. Now, if we look, the first 3 digits are significant. So that's where we're going to round up to. This is because 1, 4, and this 0 are significant because the 1 and the 4 are non-zero digits. And this 0 is also significant because it's sandwiched between non-zero digits. So therefore, we're going to round this into 1, 4, 1, 0, 0. So now we get 14,100. Now, another way we can annotate this, actually, is using scientific notation. If you don't know about scientific notation, there'll be a later video on this concept. We're going to count 1, 2, 3, 4. So therefore, we can actually give our number in scientific notation instead of 1.41 times 10 to the 4th. Let's take a look at this number. Now, this number, we know we're going to use the Pacific rule because the decimal point is present. That means everything after this is going to be significant. But that's no surprise because all these are non-zero numbers. We can ignore these zeros as they're not significant. So here I should be using scientific notation. 8.5, and now I can round this up to 8 times 10, and now let's determine how far 10 needs to go. 1, 2, 3. So because we're going the opposite way, it's 10 to the negative 3. So now we get 8.58 times 10 to the negative 3, following those 3 significant figures. So look at 2.2222. Very repetitive on this one. Now, all these numbers are significant because they're non-zero digits. So let's round up to the first 3, like we should. And therefore, we're going to get 2.2. Now, let's take a look at 873.45. Same applies here. All of these numbers are indeed significant because they're non-zero digits. Now we can just round up 873, 3 digits, and that's fully rounded right over there to our 3 significant figures. Not so bad so far. Now let's go into multiplying and dividing. This is where it gets slightly more complicated. So you want to round the answer to the same number of significant figures as the least number of significant figures in the problem. It's a lot of words, but it's very simple. This has 4 significant figures because they're all non-zero digits. These are also all non-zero digits. So we have 1, 2, 3, 4, 5, 6. Which number is less? The 4. Therefore, our answer is going to be rounded up to 4 significant digits. Now, using a calculator here, 8.888 times 3.45321 is going to equal 30.692113 dot dot dot. Okay, we're going to round this up to 4 significant digits because that's the least amount within our problem. So this significant, this also is because it's sandwiched between non-zero numbers. The 6 and the 9 are all significant. So therefore, it's going to leave us with 30.69. Okay, now we're fully rounded up. So I connect that 0, 30.69 is going to be our final answer. All right, let's take a look at the next one. So 88359 divided by 3. So 88359 has how many significant figures? Well, 5, because they're all non-zero digits. The 3 has how many significant figures? Just 1. Now, if this was a 0.0, then it would be 2, but that's not the case here. So 88359 divided by 3. So let's take a look with the calculator. 88359 divided by 3. I'm going to get 29,453. Okay, well now we have to round up to the least number of significant figures. In this case, it's just 1. So how are we going to round up 29,453 to just 1 significant figure? Well, this is why it's important to know scientific notation. So we're just going to have to do 2 times 1, 2, 3, 4. Now, because the 9 carries over, now we have 3 times 10 to the 4th is going to be our final answer. And again, this is because 3 has the least number of significant digits, so therefore my answer has to be rounded up to the least number, 1 significant digit. Adding and subtracting is slightly different. This time we're going to be looking at decimal places. So 340.05 plus 320. We don't have to look at significant figures when we add and subtract necessarily. We just know this has 2 decimal places, and this has 0 decimal places. Since we're going for the least number here, the 0 decimal places is how many our answer should have. So using the calculator, 340.05 plus 320 is going to equal 660.05. And we want this to round up to 660 because we want the least number of decimal places, which in this case is 0. Let's look at another example. 45.789 plus 24.5. Now 24.5 has 1 decimal place. 45.789 has 3 decimal places. Since we're going for the least, our answer is only going to have 1 decimal place. Not no decimal places, but just 1. So plug this into the calculator. 45.789 plus 24.5. So my raw answer is going to be 70.289. Okay, now I just want 1 decimal place, so the 8 carries over into the 2. Therefore, I'm going to get 70.3 as my final answer. since we're only rounding up to 1 decimal place. Okay, so let's get a little practice into this. So try this on your own, maybe pause the video, write this down on a piece of paper, and then come back to check your answer. Okay, hopefully you paused the video by now. So let's work through these problems. So 12.5849 plus 2.4. So 12.5849 has 4 decimal places. Since this is adding and subtracting, we're only going to be looking at decimal places. 2.4 has only 1. So now let's add this all up. Plus 2.4. So I'm going to get a rather large number. 0.9849. Now we're only rounding up to 1 decimal place. So therefore, this is going to be 15.0. Because the 8 is going to carry over into the 9, turning this into 15. Now the answer would be wrong if I just put 15, because there are no decimal places in this case. We need 1. So therefore, it's super important to remember to keep that decimal place, even if it's just a 0. Now let's move on to the next one. 432.5 minus 24.3984. All right, so there's 1 decimal place here, and there's 4 here. So let's carry out the arithmetic. 432.5 minus 24.3984. Okay, another large number, 408.1016. Okay, 1 decimal place, because that is our least number in addition and subtraction. So therefore we get 408.1 as our final answer. So hopefully this is starting to make a little bit more sense in your head. Now here we're dividing, so we're using a different rule. Now we're going to round our answer to the least number of significant figures. So therefore we need to determine how many significant figures each part of the equation has. Well, these are all non-zero digits, so therefore there are 5 significant digits in this number. Now this is 140. Because the decimal point is absent, we need to investigate into this 0. Using the Atlantic rule, everything on this side from the Atlantic side is going to be significant. So therefore, this number only has 2 significant figures. So our answer should only have 2 significant figures. All right, plug this into the calculator. 974.59 divided by 140. Well, we get 6.96 blah, but we're only rounding up to 2 significant digits. So therefore, we're getting 7.0. Again, because the 6 carries over into the 9, turning this into 7, our answer would be wrong if we didn't include that 1 0 next to the decimal point. So if you put 7, it was a nice attempt, but not quite there. Don't forget, significant figures are important here in your calculations. Okay, let's try 246 times 1.5. Because we're multiplying, we're going to use significant figure rule. 1.5 has 2 significant digits because these are both non-zeros. 246 has 3 because all of those are non-zeros. Therefore, 246 times 1.5, I get the number 369. This is 3 significant digits. The least amount in our problem is 2. So we need to round this to 2 significant figures. So we need to use scientific notation here. 9 carries over into the 6, turning it into 370 technically. But we're going to turn this into scientific notation. 1, 2, 10 to the second. Now this is just much easier because you don't really have to think about significant digits that much to determine how many significant digits you're using. So for example, if I use 370, that would also be correct in this case if I don't include a decimal point, because we'd be using the Atlantic rule, and only the 3 and the 7 would be significant, so therefore there are 2 significant digits here. So therefore 3.7 times 10 to the second and 370 are equal in number of significant digits. However, I recommend sticking to scientific notation. Otherwise, you're going to have to think about how many significant digits you have after rounding, and it can get a little tricky from there. So there's less room for error if we use scientific notation. All right, and that is it for our practice. Thank you so much for watching, and if you have any questions, drop a comment.